Okay, ladies and germs, I said I'd do a video about the river problem, and here it is. The river problem is a classic problem in physics. Oops, I just banged into my tripod. Okay, yeah, this will have to do. All right, so the river problem, we draw a picture of a river as seen from above. So there's the far bank and the near bank of the river, and the river is going to be some width at this point. I'm just going to go ahead and call it 200 meters across. 2 football fields, that seems reasonable for a river. This river, however, has a current flowing in it, and the current is going to be 1 meter per second. Now we are in a boat on one shore, and we are going to try to go to the other shore. This boat is capable of doing 10 meters per second through the water. But since there's a current, that is not the direction that the boat is going to go. The boat is going to go 10 meters per second directly across the river, but the river is moving as well, so the path, as seen from a drone above, would be at an angle over here, and we are going to miss. We are going to miss our intended landing zone by some distance x, as long as we don't correct while we're driving, as long as we don't notice that this is happening and change the steering. So pointed straight across the river at 10 meters per second. We're going to go over here. There are 2 ways to solve this problem. One is a purely vector way. And the purely vector way to do it is to make a drawing of the velocities. You see, the velocity of the boat is an arrow that represents 10 meters per second going across the river. And the velocity of the river is an arrow representing 1 meter per second, a significantly shorter arrow, and that's going to the right, or the east, I guess. And so our actual resultant velocity will be that right there. And we can find the magnitude of that resultant velocity, and we can find its direction. But it is tied to another triangle. This triangle is a triangle, this is the triangle of velocity. It is tied to a triangle that is a triangle of distance. Because, of course, the distance across the river is 200 meters, and the distance that we're going to miss our target by is x. And this is a similar triangle. What is this distance over here? Well, that's the distance we actually travel. I'm not sure we're interested in that, but the point is that this angle right here and this angle right here are exactly the same angle. The velocity produces the displacement, therefore the triangle of distances. So that means that 1 is to 10, the speed in the x direction is to the speed in the y direction, as x is to 200. That's a feature of similar triangles. And so now we can just go over here and say 200 meters times this ratio of 1 meter per second over 10 meters per second equals x, and the distance we're going to miss by 200 times 1 divided by 10 is 20 meters. That's the vector way to solve this problem. There's another way to solve this problem, and I'll do that over here, and that is to talk about it in terms of motion. Now, this is not projectile motion. Projectile motion has acceleration in the y direction and no acceleration in the x direction. This is just a motion problem where we have compound motion. We have motion in the y and x directions, and neither one of them is accelerated. In that case, the Swiss Army equation is x equals vx times t for the x direction, and y equals vy times t for the y direction. And there's no initial or final, and there's no acceleration term because there's no acceleration going on in this problem at all. So this would definitely help us find how far we miss our target by if we just knew the time. But as we do with projectile motion problems, we can solve the y equation for time. And y, the distance we're going to travel in y, is going to be 200 meters, and that's going to equal our y velocity, which is 10 meters per second, times t. So 20 equals t. 20 seconds equals t. And now we can use that over here to say x equals our velocity in the x direction, which happens to be 1 meter per second. And then we multiply that by 20 seconds of time, and we get the answer again that we miss our intended target by 20 meters. So we had to do this one first, even though it's to the right on the paper, and we had to do this one second. But either we treat this as independent motion in the x and y direction, or a compound motion, or we treat it as a vector problem with similar triangles for the velocities and the distances. That is how to solve the river problem. Now there's an advanced part of the river problem that asks where do you need to point the boat in order to go straight across. And I will tell you that that is a little more difficult problem to solve. Many people think that what you should do is you should just aim the boat the same distance x upriver, and then you'll arrive at your destination. And that doesn't work, because once you point the boat the same distance upriver, then what happens is you are not going across the river nearly as fast. You have a lesser component of velocity across the river, so you're in the river for more time, and you will actually still miss a little bit downriver of your intended target. The way to solve this problem really goes back to the vector nature of it. See, what we want is we want to point the boat in some direction at 10 meters per second, so that this component of the boat's velocity is exactly equal to 1 meter per second. Thus, the resultant velocity of the boat will be straight across. That's what we want. We want to create this triangle where our 10 meters per second is aimed off to the side, and we have a component of velocity upriver that's 1 meter per second that exactly cancels the current out, giving us a resultant direction here. So our distance triangle would look the same, and we would go straight across the river. And this triangle is all we need to do is find this angle. That's what we need to do. And this triangle lends itself to using sine to find the angle. Sine of theta is equal to the opposite side, which is 1 meter per second, divided by the hypotenuse, which is 10 meters per second. So that would mean that theta is the inverse sine of 1/10. And so we can figure out what angle you'd have to point the boat in order to go straight across the river if we just own a calculator. Second function, sine, parentheses, 1 divided by 10, end parentheses. And that's a 5.7 degree angle, which is not the same angle you would get here. Just for excrement and giggles, let's find out what this angle would be. For this angle, we would probably have to use tangent. We would say that tangent of theta equals the opposite side over the adjacent side. So we need to take inverse tangent of 1/10. Now, for small enough angles, those two things are very nearly the same. 1 divided by 10, end parentheses, and that is also a 5.7, but it's 5.71. Ha-ha, he said. Yeah, like I said, for small angles, those are almost the same. So anyway, this is the river problem, and if I was going to do this video again, this is a slightly different problem than that one. I would get an extra digit on this 5.7 so that we could compare these two and show that they're close but not exactly the same. All right.